Hello, everybody. We're going to wait a minute. We're going to start at basically 1 minute past the hour. We're letting people filter into the Zoom room. Okay, welcome everybody to another one of our Green Bank Observatory community Zoom events. My name is David Frayer. I'm just going to give a quick observatory update during the presentation. Please put your questions into the chat window as a reminder. And so very quickly, I'll be giving this for Karen, our director, who could not attend today, and Jay will be introducing our speaker, who's coming all the way from the Netherlands. So the COVID status, people are still getting vaccinated, slowly but surely, hopefully. And a lot of us are getting back to work. Most of our staff are vaccinated, and a lot of us are at work. I'm at work now. It's really nice getting back to work. As more and more people get in, we expect to get back to full operations on September 1st. They're still doing outdoor tours, the Science Center. The telescope itself is still running 24 hours, 7 days a week. We do have our summer maintenance plans, they're ongoing. We have upcoming community Zoom events. They're on our web pages. Just as a reminder, we have the Single Dish Summer School that's in September. Also, the upcoming proposal deadline will be August 2nd, the first Monday in August. The call for proposals should be coming out in early July. And with that, I'm gonna hand this over and I'm gonna stop sharing my screen and I'll let Jay introduce our speaker. So welcome everybody. Let's see here.
Thanks, Dave. Sarah, you wanna begin sharing your screen?
Yes.
Thank you. Our speaker today is Sara Issaoun from Radboud University in the Netherlands, and talking about the size, shape, and scattering of Sagittarius A star. Thank you. And please put questions in the Q&A.
Thank you very much. So thank you for inviting me to talk about our project. You know, the GBT plays a big part in our science, and it's really great to be here and talk to you all about it. Okay, so millimeter VLBI is a perfect tool to understanding supermassive black holes. You know, I do a lot of my work as part of the Event Horizon Telescope, and I also lead this 3 millimeter or 86 gigahertz observations of Sagittarius A star I'll talk about today. So what is millimeter VLBI used for? For EHT, it's used to test theories of gravity in the vicinity of a supermassive black hole, to connect horizon scale physics to launching mechanisms of relativistic jets, and connect horizon scale physics and dynamics to multi-wavelength variability in flares. So the supermassive black hole in our galactic center, Sagittarius A star, is one of the prime targets to do this kind of science. It is the closest supermassive black hole to us. Its mass and distance are known very precisely, thanks to the Keck UCLA group and the gravity collaboration work with the stellar orbits. So what does Sagittarius star actually look like in the radio? We expect the size of the shadow of Sagittarius star to be about 50 microarc seconds or 5 Schwarzschild radii based on past proto-EHT measurements. But in order to test theories of gravity, not only do we need to know its mass and distance precisely to determine its size, we also need to know its orientation, whether it has a spin, and what is the origin of its emission mechanism. So there's a long-standing debate about the emission process dominating in the radio. Is it coming from the accretion disk around the black hole or from the jet or outflow? So of course, the Event Horizon Telescope is the best way to see the Sagittarius star shadow up close. And we're working very hard on these efforts. But the EHT doesn't actually tell us the whole story in understanding Sagittarius star. So this is the spectral energy distribution of Sagittarius star. So this is the flux density as a function of frequency. We have this radio millimeter band slope in the infrared detections here. And this slope is actually, very typical, typically modeled in theory simulations with an accretion disk and a jet component. So it is very hard to get this, this slope from optically thick to optically thin without a jet or outflow simulated. But in our images of Sagittarius star in the radio, we've never seen a jet. There doesn't seem to be any sort of elongation in any direction where jets would be apparent, like we see in extragalactic black holes. So the origin of the radio emission in Sagittarius star is still unknown, and at 1 millimeter, unfortunately, or fortunately for GR, but unfortunately for us trying to understand its radio emission, the shadow is really the dominating feature. So if we have these two different emission models, this is an accretion disk dominated emission, this is a jet dominated emission. As you can see, they look very similar. So the shadow and a crescent is what you would see if you would image these with the EHT. So really gravitational lensing is the predominant feature dominating the image. So if you want to learn about the accretion flow properties, maybe you'd want to zoom out a little bit and see kind of more of the optically thicker gas around it and see if that actually tells us anything about the origin of this emission. So whether the morphology is more disc-like or whether there's an elongation that would tell us about a jet. So if we zoom out, we end up at 3.5 millimeters or 86 gigahertz. And here accretion flow differences are more apparent. So the accretion disk dominated model is more spherical, more symmetrical, and the jet dominated model is a lot more elongated. And if we go to longer wavelengths, of course, the jet will become more and more elongated, but we actually go beyond the realm of these general relativistic magnetohydrodynamic simulations that are able to simulate the black hole environment and the gas very accurately. So 3 millimeter is actually our Goldilocks region to understand accretion flow of Sagittarius star. But that's not all. Unfortunately, we're in our galaxy. So we're looking through our whole galaxy to see the galactic center, and we're subject to interstellar scattering. And this is stronger with increasing wavelength. So although it may not have such an effect for EHT, at 3 millimeters, it really has an effect. So these are the exact same models again, and these are actually movies. You can see them flicker a little bit, the same movies as before, except we've added the effects of scattering on top of it. And we're back to square one, really. They look exactly the same for just human eye. We wouldn't be able to tell which one is the accretion disk dominated and which one is the jet dominated. So actually understanding properties of the interstellar scattering is really crucial for 3 millimeter observations, because if we could understand the properties of the scattering across the entire waveband in the radio, we could remove the effects of scattering and reconstruct an intrinsic structure that would then tell us this morphology, whether it's more accretion disk or more jet. So what do we know about scattering so far? We've had several decades of observations of scattering in the galaxy. We know that the scattered size of Sagittarius star on the sky scales with lambda squared. So this is size as a function of wavelength. And we know that at 3 millimeters over here, the intrinsic size, so Sagittarius star intrinsic size starts being comparable to this blurring kernel that blurs the source predominantly in the east-west direction. And at 1 millimeter, the intrinsic size dominates. So this is why at 1 millimeter with the EHT, we can attempt to actually see the black hole shadow. It will not be completely blurred out by scattering. But also in the centimeter wave, we detected what we call refractive substructure. In the Fourier domain, it's called refractive noise. So it appears as this kind of long baseline, small scale detections in the image, which in the centimeter wave, they cannot come from the intrinsic source. They're actually little contaminations or structure in the scattering screen itself. And these contaminate the image as well and produce spurious signal at high resolution. And so how do we extrapolate this signal we see in the centimeter wave to 1 millimeter for EHT, for example? How can we look at 1 millimeter long baseline or high resolution detections and actually know whether it actually is intrinsic source or whether it's contamination from the scattering? So this is a very non-trivial problem that we need to understand. And this extrapolation is definitely not a simple thing to do. So there's more to worry about. So depending on scattering theory, interstellar scattering can contaminate our tests of GR with EHT. So we have two scattering models, one we call J18 and one is GS06. They have properties that fit all radio observations of Sagittarius up until 2017. And what they do to EHT images is very different. So here we have a simple ring at 1 millimeter, unscattered. Now I'm going to scatter it with these two models. So this ring scattered with the J18 model would look something like this. So we have this blurring predominantly in the east-west, and we have small levels of scattering substructure or refractive substructure on top of it that add these small contaminations. So J18 has small levels of refractive noise. The GS06 model has large levels of refractive noise, and this is what it does to the ring. So still, this blurring in the east-west, but the refractive noise or refractive substructure distorts our image to such an extent that it is impossible to recover the shape of the ring. So if this were what we would see with EHT images, we would have very little hope to reconstruct a shadow. So at 3 millimeters, they also, again, look very similar in the diffractive blurring sense. They have the same blurring kernel. Both scattering models have the same blurring. But in the refractive noise, refractive substructure, they're different again. So for the J18 model, you see low levels, and for GS06, very high levels of substructure. And if we could have a 3 millimeter experiment that could pick up on long baseline refractive properties, so high resolution, we would be able to tell these two apart, and we'd be able to tell what we would expect for EHT. So the perfect experiment is VLBI with the global millimeter VLBI array, or GMVA, and ULMA. So in 2017 and 2018, we did two sets of observations. In 2017, we had the European millimeter wave facilities, the Very Long Baseline Array, the Green Bank Telescope, and ULMA. And for 2018, we only had the stations in the Americas, so without the European stations. And ULMA was really a game changer for north-south coverage, particularly because that is the direction we expect the scattering to be weakest and actually pick up on intrinsic structure, and also long intercontinental baselines to get detections on higher resolution. So we observed a single observation of 8 hours with a full imaging array, which we call our imaging observation in 2017. And then our time domain observations in 2018, which are two observations separated by 3 days of 6 hours each, to explore the dynamics of refractive scattering. This is what our amplitudes look like. This is our correlated flux density as a function of projected baseline length. So at short baselines, we expect the source to look Gaussian. And at long baselines, everything past this point are all new detections we've never had before with ULMA. And we have here to guide the eye these two curves, major axis and minor axis of a source on the sky that is Gaussian. And this is because pre-2017, Sagittarius has always been modeled as a Gaussian source on the sky. And now we actually have evidence that it is not a Gaussian. So the first line of evidence is, of course, these ones. The ULMA GBT baseline is our most sensitive of our array. We have pretty amazing and unprecedented signal to noise. We've never had a 3 millimeter before on Sagittarius. And you can see that ULMA GBT in the orientation, it actually lies along the minor axis of the source, but it has a flux density that is higher than what is expected for a Gaussian minor axis. So it's supposed to sit down here, but it actually sits up there. So it tells us already just by looking at ULMA GBT that the source is non-Gaussian on the sky. Then we have these other baselines to ULMA to VLBA, which tell us either probe levels of refractive noise. So it's either purely refractive noise or a mix of intrinsic structure and refractive noise. We can't yet separate those. So across our 2 years, we have persistent non-Gaussian structure and persistent low levels of refractive noise that are consistent with the J18 model and much lower than GS06. So now, assuming the J18 model, we want to make an image. So we reconstruct an unscattered image using a tool called stochastic optics. So it's basically adaptive optics, but in post-processing. So if we have an image there's a diffractive blurring part that stretches it in the east west, and then there's refractive noise that adds substructure to the image. So we have this scattering kernel and this varying refractive noise. So we solve for a varying phase screen that contains these refractive noise structures, and then we remove them, and then we deconvolve our source with the scattering kernel to get an intrinsic source. So this is what we get for image. We have our scattered image on the left and unscattered on the right. We get a source of about 120 by 100 microarcseconds for the unscattered, which tells us that the emission at 86 gigahertz is about 12 short shield radii of the black hole. And we have consistently zero closure phases, which tell us that there's no asymmetry. We tested the shape of our image against different simulations. We looked at different electron acceleration in disk and jet models, different electron heating, and even spin. What we found is that our image is highly symmetrical compared to jet-dominated images, so that depending on inclination, some jet models are ruled out. So emission must be face on less than 20 degrees if they're jet dominated. So anything elongated like these are ruled out. Then ALMA detections at 3 millimeter rule out this GSO6 scattering model because their refractive noise is too low. There's about a 1 in 100,000 chance that it is the GSO6 model based on our 2 consecutive years of observation. So we can rule that out pretty safely. And this is really encouraging for EHT science. We also compared our results with longer wavelength constraints. We found that comparing to 13 and 7 millimeter constraints of the scattering model and the ALMA GBT flex gives us a source size about 100 microarcseconds. This is purely just from model fitting. And we also directly modeled the intrinsic source and the scattering parameters of the model that gave us, again, a source size along the Magner axis of 100 microseconds, which is consistent with the longer wavelength predictions. And the scattering parameter space we have overlaps with the longer wavelength constraints, which actually taught us that a single scattering model can actually explain behavior in both the centimeter and the millimeter regime. In the future, we want to expand GMVA plus ALMA to more sensitive stations. So we want to include more stations in Europe, in Hawaii, and in America. We want to get highly sensitive triangles. Our main one that we're really interested in is ALMA to GBT to LMT, which is in the north-south direction. It's amazing sensitivity because the LMT is a 50-meter dish. So adding to GBT and ALMA would get very sensitive measurements of variability to look at orbiting structure in the accretion flow. So I can leave my summary up and stop here for questions. Thank you very much.
Thank you very much. We have a couple of questions. Let me remind everyone, if you have questions, put them in the QSA. I think the one that's relevant is how much of the electron scattering arises near Sag A star?
Right, so that is a great question. And that is one I think we were able to answer around 2015 when we were able to measure or determine the location of the scattering screen. So the scattering screen actually lies in between us and the galactic center. I think it's about 3 kiloparsecs away from us and 5 kiloparsecs away from the galactic center. And we know this because of the scattering properties of this magnetar in the galactic center that is about 2 arcseconds away from Sag A star on the sky. So by kind of looking at common properties between the two, we can determine or triangulate the location of the scattering screen. So that is where we placed it.
And here's another question. Is there any prospect of using the Greenland telescope at 3.5 millimeters?
Right, yes, Greenland does observe at 3.5 millimeters. It is a component now of the global millimeter VLBI array. The disadvantage with us is that it does not observe Sag A star. And so for us, it doesn't really add that much to the array. But I think it is much too low for Sag A star. But it definitely does observe as part of the global millimeter VLBI array. So if people are interested in having GLT as part of your experiments definitely do propose for that.
There's another question. In the very first graph of energy distribution, the spectral index was positive for radio observations, while it was negative in the infrared. Is this behavior expected? What can be understood by this?
Right. So this is the spectral turnover here in the terahertz is definitely expected for the current model of accretion flow around a black hole. So we have this radio part that is illuminated by the accretion disk and the jet. And then as it becomes more and more optically thin, you reach this what we call the submillimeter bump. And then it becomes, you get this turnover here in the infrared.
So I have a question about your 2019 paper, and you listed a result from that in your conclusions, which basically limits the line of sight angle of any jet from Sag A star.
Right.
Is there a jet from Sag A star?
Yeah, so that is a really good question, and one we haven't yet been able to fully answer. I think there are multiple ways to determine this, at least from our image from 2017, which is again a single instance in time. And it may have an intermittent jet that may come on and off, which we still don't know. But from that instance in time and from the structure we inferred from 2018, it seems like it is a very symmetrical source. And so if it did have a jet, it would be in the direction, it would be pointed more or less towards us, which doesn't mean it doesn't have one. And there is evidence that there is an outflow around Sag A star based on time lag observations of flares in the radio. So if you look at flare time series of flares and you look at them at a function of frequency, you will see a lag between shorter and between lower and higher frequencies of the flare. And these lags don't happen if you don't have an outflow. So there is evidence that there is outflow happening near the galactic center. And now we have evidence that it's most likely pointed towards us. And the orbits in the infrared that gravity observed also seem to indicate low inclination orbits. And so I think we're starting to piece the puzzle together, and hopefully with more images, more observations, we'll be able to give a definite answer.
Okay, thank you. Another question. Would the South Pole telescope provide useful expanded north-south coverage if equipped with a 3mm receiver?
Oh yes, definitely. The South Pole would be really great to be added at 3mm. I think the difficulty is, how much there is to gain to putting a receiver at the South Pole, which is not an easy task. And right now, I think for EHT, obviously, we're focusing on having the 1 and 0.8mm because the South Pole really adds a lot to the shadow imaging. And so, yeah, it depends on how much there is to gain in terms of science in adding the South Pole, but it would definitely be in addition to the imaging.
How much might polarization measurements help? And is the signal to noise at all within the realm of feasibility of doing them?
Yeah, another really great question. So we have polarization measurements just with ALMA only, and we'd really like to get detections with VLBI. Unfortunately, with the experiments we have done in 2017 and 2018, our bandwidth is only 256 megahertz, and unfortunately that is too little to detect polarization, especially because at 3mm, it's not expected to be very strong. And so since then, though, I think VLBI has doubled the bandwidth, and we put in a proposal for next year to observe again with the doubled bandwidth and with the GBT and ALMA, and hopefully also with NOEMA joining us. So we'd have higher sensitivity and we'd have double bandwidth, and we're hoping to get polarization detections. And they're definitely the jet models and disk models have different polarization signatures. There's also different polarization signatures depending on the disk magnetization, and also different polarization signatures depending on orientation. So we'll be able to learn more from that.
Okay, we have time for a couple more questions, and here's one. Any of the data provide rotational modeling?
So as in orbiting features or as in rotation measure?
No, I don't think it's rotation measure.
So orbiting features, yeah, so any, rotational motion, we definitely don't see it. So at 3 millimeter, within a few hours of our observation, we expect the source to be static, more or less. So this is why we can reconstruct an image, a static image, because we don't expect strong motion in the data. In our data set, we do not see any variability signature, but in terms of, I mentioned these closure phases. Here's an example here. These closure phases, which if we have the sensitivity, which we would have for a triangle that contained ALMA LMT GBT, which we propose for next year, we would have the sensitivity to actually detect orbiting features if there were any to be seen. And there's really exciting possible overlap also to observing also together with gravity, for example, and look at flares that happen in both the radio and infrared, because 15 or 12 to 15 Schwarzschild radii that we see with 3 millimeter is the same regime where gravity observes the orbits, the flare orbits. So there's really interesting prospects for synergy there to understanding orbiting features.
Okay, we have time for two more, and here's the first. Is observing extragalactic supermassive black holes at much lower frequency bands possible? Will it reveal more information, provided the dispersion measures are as minimal as possible for the possible imaging candidates?
So at lower frequency, we are again in the optically thick regime. So the emission will be dominated by the accretion disk and jet. So for extragalactic sources, we would be pretty far out in the jet, which is obviously really interesting work also to do to look at time domain and polarization signatures in jet structures. I think we learn about how these jets maintain jet collimation and these different shock regions in jets that create these knots that we still don't fully understand. So there is a lot of jet science we can do with extragalactic black holes. But in terms of really understanding the connection between the black hole itself and the accretion flow, we really need to get close to the black hole. And right now we only have 2 of those. We only have a supermassive black hole in our galaxy, Side A star, and we have the one in the galaxy M87, which is big enough and close enough that it has about the same size on the sky.
Okay, and finally, I think Frank Ego, did you raise your hand? Do you want to say something? Let me allow you to talk in case you do. Nope, he's gone.
Oh, that was a mistake. I hit the button accidentally.
All right. Well, I would like to thank everyone who participated today. Thanks very much to Dr. Issaoun. And to remind everyone that 2 weeks from now will be the next in our community Zoom. Trey Wenger from DRAO talking about galactic structure, galactic H2 regions, and structure in the Milky Way. And on July 7th, Marina Brozovic from JPL talking about biostatic radar observations of near-Earth objects with Goldstone and the GBT. We look forward to you joining us then. Thank you.